Good evening, folks. Just a change of scenery here with the Flat Earth. I came across this lecture by Mr. Brian Cox. I thought I'd just play it. I'm not going to go through the whole thing. I might skip some parts, but I just wanted to talk about some salient bits about it and see how he fumbles his way through these things with all the theories and anomalies. So let's get the show going.
Brilliant to see you. Yeah, I want to talk about kind of a small goal. I want to talk about the universe, but particularly the two great pillars of our understanding of the universe that we've built over the last century. And we're still building absolutely now two of those pillars that I hope you're going to contribute to building in the future.
Notice how many times he touches his nose. And when he does, I shall play this. Body language.
Two pillars, two things that maybe you don't learn about at school, but you'll certainly learn about at university. One pillar is called relativity, which is Einstein's great contribution to science.
And also what I consider as a hoax or a lie.
The other one is something called quantum mechanics, which is theory. It seems very strange. You may have heard of things like Schrodinger's cat, things can be in two places at once. But actually, quantum mechanics is our theory of everything that happens in the universe other than gravity. And today, the place where we explore that in detail is the Large Hadron Collider at CERN in Geneva, the place that I work when I'm not messing around on television. So I want to give you some idea of what we're doing now at the Large Hadron Collider and what we hope to discover within the next year or two. So absolutely current cutting-edge research. The first thing I think to say about the ambition, because I said we want to understand the universe and our two great theories of it, is to look at the sheer size of the problem. And that's one of the things that I think captured my imagination first, when I first began to get into science, very 5, 6, 7 years old. It was the sheer ambition of it. Because this is a picture of the universe. This is actually a picture of the night sky. If any of you are interested in astronomy, there is the constellation of Orion that you can always see in the sky. But I want to focus, I want you to focus on a piece of sky that's somewhere around here. I'm going to zoom in on it now. It's a piece of sky that you would cover if you took a 5p piece and held it about 25 metres away. So imagine taking a 5p piece and putting it 25 metres away over a tiny piece of sky. Well, a few years ago now, the Hubble Space Telescope, which is in orbit around the Earth, turned its gaze to that tiny piece of sky, the 5p bit of sky, and took a picture. It opened its camera to thousands and thousands.
Now let's say the Hubble telescope isn't a camera. It doesn't take pictures. It records light. It gets converted into a picture by NASA artists, and it's re-rendered. And so what we're actually seeing isn't what Hubble sees, but it might see it in terms of radio frequency or different spectrums of light which are invisible to our eye. So I would question, perhaps, that the Hubble is looking at the firmament on a microscopic level.
Thousands and thousands of seconds, and just gathered the light from that piece of sky. It was deliberately chosen because it's a dull, uninteresting piece of sky. Actually, from the surface of the Earth, you would see
a bit like you, Brian.
Virtually nothing in it at all. But this is the picture that Hubble took. And you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in the image. And virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies, on average, have what, 100,000 million stars like...
Million? 100,000 million, did you say? That's just a guess, isn't it, really? It's not fact.
Like our sun in them, at least.
Like our sun in them, at least. You don't know, do you?
So 100,000 million stars.
100,000 million. 100,000 million. How do you know that? It's a guess.
in each one of those 10,000 blobs. The most
So they're just blobs now, are they?
distant object in that image, and I'm going to talk a bit about how we know these things in a moment, but the most distant object
Oh, I'm looking forward to that, Mr. Cox.
is 13.2 thousand million light years away. It was
What was that? Really?
actually discovered in this image only a few months ago. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. That's a tiny, remember, 5 pence piece of sky 25 meters away. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. I'm going to show right at the end of the talk that we think we're beginning to understand where that structure came from.
You think where that structure came from. It's the best guess, isn't it? It's the best guess. And you're actually going to actually give the own evidence that it says it's a guess in a minute.
Just to get some sense of scale, that little line up there, you might not even be able to see it at the back, but that's the 1 billion light year line. The light takes 1 billion years to travel from one line to the other. This is the observable universe. And I'm going to show you, there's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars that we think are in the we know from observation are in the observable universe at the moment.
You think
30,000 million
squillion, trillion, zillion, gazillion, million, zillion, million. It's a guess.
Stars. It's like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies.
Million. Just like your bank account, eh, Mr. Cox?
That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, a blob from which light is.
I can see a blob right in front of me spouting a load of nonsense. That's the biggest blob I can see.
Had chance to travel during the history of the universe. So the universe is big, is what I wanted to say to you. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people.
Wasn't he a pedo?
People who can't remember where they put things. It's enormous. So how can you... Oh, I don't want to start that yet. There we are. So how can we possibly begin to think about explaining that? You know, how do we know, first of all? How do we know it's so big? How did we find that out from this planet that we're standing on now? And how could we begin to make theories, guesses, I suppose, if you like, about where that came from?
You said it. How do we begin to come up with the theories? So it still is all theories. You're right, for once.
How it began, how fast light travels, all those facts that I've said to you, or all those numbers that I've given you, best estimate of how the universe works. It is, of course, science. And I want to play you a little video of, for me, what the best definition of science or the scientific method that I've heard comes from a very famous physicist called Richard Feynman, who won a Nobel Prize for building one of the first quantum theories of electricity and magnetism. It's called quantum electrodynamics. This is back in the 1940s and 50s. It's our best theory today of how light interacts with matter. But Feynman was also, I recommend that you read his books. He was a brilliant teacher, a brilliant lecturer as
Missed that one, sorry. There we are.
well as a Nobel Prize winning physicist. And he gave this lecture back in, I think it was the 1960s, and it's just a 1-minute definition of the scientific method.
I'm going to discuss how we would look for a new law. general, we look for a new law by the following process. First, we guess it. Then we no, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience.
Okay, to nature we compare with experiment and experience.
Compare it directly with observation to see if it works.
Observations. Thank you, Mr. Feynman.
If it disagrees with experiment, it's wrong.
If it disagrees with experiment, it's wrong. You sure you wanted to use this, Mr. Cox? Because this guy's right.
In that simple statement is the key to science.
Did you hear that? That's the key to science, not theoretical bullshit.
It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
That's all there is to it. Where's your experiments, Mr. Cox? And where's your graphs that you show? And little plums for your gravity?
So I think that's a really beautiful description of what science is. It's really very simple. It's the application of common sense in many ways.
Well, you don't seem to be spouting much of it. You're just spouting drivel.
What it is looking at the universe, looking at nature, guessing about how it works, seeing what the consequences of that guess are, testing those against nature, and as Feynman said, the great power of science. It doesn't matter who you are. There's no such thing as authority in science. If your guess disagrees with nature, then it's wrong, and that's all there is to it. Easy to say, but how can we possibly compare ideas about the origin and evolution of the universe with nature? Well, if you think about it, there's only one way to look into the wider universe from Earth, certainly the universe beyond our solar system, to gather the light from distant stars and planets. And there is an immense amount of information contained within that light. This is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic.
Sorry, I think I stopped that in the wrong place. Let me just smidgen it back slightly, because I think he said it was actually CGI.
Distant stars and planets. And there is an immense amount of information contained within that light. This is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic. It's a real movie of the sun taken by an orbiting spacecraft that just observes the sun every day.
So why don't you tell us the name of the satellite? Is it Discover? Is it Soho? That's from 2000, 17 years ago. So why couldn't you just tell us what the name of the satellite was? And
you see that it's a dynamic and violent place. You could fit 1 million Earths inside that ball of glowing plasma, by the way.
Ball. Did you hear the way he accentuated the word ball?
1 million planet Earth.
Million squillions.
It burns 600 million tons of hydrogen
fuel
every second. So it's a powerful, gigantic object. Many years ago now, stretching back to Newton and before, we looked at the light from the sun, and after Newton, we found a way of analysing it by splitting it up into its component colours. Prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. And this is a picture, a modern-day picture of that rainbow. Now, rainbows, of course, lots of different colours from blue all the way to red. But when you look at the light from the sun in a laboratory, and you're very careful, and you put it through a very precise prism.
Do you need to look at the sun in a laboratory? Surely the outside world would be good enough. Simple and amazing.
Then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, if you want, of the chemical elements themselves.
Well, I've never seen that in a rainbow. Maybe the precise prism has special glass which creates the lines. I don't know.
What happens is you'll know that an element is a nucleus with
You'll know that for sure, yes.
electrons going around it. And each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere, so elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to moving the electrons around in very specific ways. So, for example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. Why? Because of the way its electrons are arranged around the atom. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of.
So we're talking electromagnetics then, aren't we? Electromagnets. Everything has sort of electromagnetism, possibly with electrons.
But also, and this is the point for looking at the wider universe, something very interesting happens when you look at these spectrum, these black lines in the rainbows of the most distant stars and galaxies. So here's a distant galaxy. You can see the light from that galaxy. What you find, of course, is that the spectrum is the same.
What you find, of course, as if we've done these so-called experiments. What you find, of course. Yes, he's saying, of course, like, you know.
The black lines are all the same because chemical elements are the same across the universe, except that in all distant galaxies, the lines are shifted. They're moved. They're not in exactly the same place. Now, one explanation for that, of course, could be that the elements are somehow...
One explanation of that could be, it's not a definitive statement, Mr. Cox.
...different in different parts of the universe. But it's interesting, isn't it, that they're all shifted in the same way. And actually there turns out to be a pattern to this shift. So what's the explanation? Well, the explanation for the shift is very simple. The universe is expanding. So if you look at the very...
Based on a considered opinion.
Distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys.
So if the universe is expanding in all directions, then how come we don't see any streaks of distant galaxies streaking through the sky as it's moving left to right and up and down?
Journeys from the distant galaxies to us. What does that do? Well, it stretches the light. So the wavelength of the light is stretched. The wavelength is the colour. Red light has got a bigger wavelength than blue light. So as the light, let's say it comes from a star, it's a hydrogen, let's say, emits a line up here, and that journeys across the universe to us, it gets, actually, let's start in the blue. So let's say there's an element down here that emits light in blue. It journeys across the universe, it stretches, it stretches, it stretches, it moves towards the red bit of the spectrum because it gets stretched. Lovely. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. That's one piece of the puzzle. So just qualitatively you can say that tells us our universe is stretching. Space itself is stretching. How do you quantify that though? Well, this is in many ways even more fascinating. You see, there are certain types of objects, certain types of phenomena that occur out there in the universe that we know the brightness of very accurately. Now, imagine how useful that is. If you know how bright a light is, and you put it somewhere a long way away, and then look and see how bright it looks to you, then you can work out how far away it is. It's very simple. Obviously, it gets dimmer and dimmer the further away it is from you. Now, this is a picture of one of the types of object that we know the brightness of very accurately, and it's actually this one here. Now, this is a beautiful picture. This is the galaxy. So this is an island, as I said, of 100,000 million, perhaps 200,000 million stars like our sun. There are perhaps a billion stars in the centre of
millions and millions and hundreds of billions and millions.
This galaxy shining brightly. This looks like a star that must be closer to us than that galaxy because it's so bright. It actually isn't. It's actually something called a supernova explosion. This is a star in the galaxy. It's on the edge of the galaxy. It's the same distance away as the billion or so suns in the centre and 100 billion or so.
Billions and millions and billions. Oh, enough of this. Okay, just give him one more. There we are. Thank you very much.